The siege of Pavia in 1525 saw the debut of 50 carri armati, or armored wagons, which shattered 3 lines of French infantry before breakfast, their multi-directional cannons clearing swaths of soldiers. By 1530, textile guilds in Florence, using da Vinci's automated looms, quadrupled their silk output, flooding European markets and causing the price of luxury fabrics to plummet, making them accessible beyond the highest nobility. Venetian engineers, employing da Vinci's diving bells and breathing apparatus, began constructing submerged harbor defenses in 1515, rendering traditional naval blockades nearly impossible against the Serenissima. By 1520, a network of signal towers, equipped with Leonardo's improved optic lenses and staffed by trained aviator scouts, could relay urgent messages across the Italian peninsula in under 6 hours. Number 7. The sky was no longer the limit. Leonardo da Vinci's fascination with flight, meticulously documented in his notebooks, with sketches of flapping wings and spiral air screws, did not remain confined to parchment. Around 1505, with patronage from a forward-thinking Florentine merchant, collective eager for an edge in communication and reconnaissance, workshops dedicated to constructing macchine volanti, or flying machines, began to appear. These were not the workshops of lone inventors, but bustling centers of skilled artisans, carpenters, sailmakers, blacksmiths, and clockmakers, all working from simplified, producible versions of Leonardo's designs. The first successful man-powered ornithopters, relying on the pilot's strong legs and arms to pump wing-like structures, achieved sustained flight for several hundred paces in 1508. These early flights were perilous, low to the ground, and often ended in undignified but rarely fatal tumbles, thanks to another of Leonardo's concepts rapidly put into production: the parachute. Initially a crude pyramid of linen, these life-saving devices became standard issue for all piloti. The immediate application was military. Scouts, launched from hills or temporary wooden towers, could gain a bird's-eye view of enemy encampments or troop movements, sketching furiously onto small pads of paper. These sketches, often rough but incredibly valuable, were then flown back, or, if the scout landed within friendly territory, delivered by fast horse. By 1512, the Republic of Venice, ever watchful of its trade routes and rivals, established the first Corpo dei Piloti Esploratori, a corps of scouting pilots. These men, trained in secret on remote islands in the lagoon, used gliders launched from ships to observe naval movements far out at sea. Messages were relayed back via carrier pigeon, or, if close enough, by coded signals, using flags, another area where Leonardo's insights into optics and signaling were applied. Communication between cities also underwent a transformation. While the ornithopters were too fragile and their range too limited for carrying significant cargo, they excelled at carrying small vital documents. Posta, allata, or winged mail, became a premium service. A letter from Florence to Siena, a journey that could take days by conventional means, arrived in a matter of hours, if weather permitted. This speed revolutionized diplomacy and intelligence gathering among the Italian city-states. Wealthy banking families like the Medici and the Strozzi maintained their own small fleets of ornithopters and pilots to expedite sensitive financial instructions and market information. The development of the aerial screw, Leonardo's precursor to the helicopter, proved more challenging. Power-to-weight ratio was an immense hurdle for Renaissance materials and human strength. However, smaller, unmanned versions, powered by tightly wound springs or rudimentary clockwork mechanisms, were used as elevated observation platforms, tethered like kites, but offering a more stable view than a man buffeted by wind in an ornithopter. These caicosciol volanti, flying snails, as they were nicknamed, often carried mirrors, angled to reflect sunlight in coded flashes, creating a network of aerial signal stations. Culturally, the impact was profound. The sight of men in the air, even briefly, captured the public imagination. Festivals and public celebrations increasingly featured demonstrations of flight. Artists, always keen for new perspectives, began to depict landscapes and cityscapes from above, a viewpoint previously only imagined. The very notion of human limitation was challenged. Churches and scholars debated the theological implications of man taking to the domain of birds and angels. Some saw it as hubris, others as a divine gift of intellect. Production of these machines spurred innovation in lightweight materials, stronger fabrics for wings and parachutes, and more efficient gearing mechanisms. The demand for skilled pilots created new professions, and the casualties, though minimized by parachutes, highlighted the inherent dangers and spurred further safety innovations. By 1535, the sky over Italy, while not crowded, was no longer empty. It was a new frontier, actively being explored and utilized, all stemming from the dreams of one man and the workshops that turned those dreams into tangible, if sometimes rickety, reality. Specialized schools for aeristi emerged, teaching not just the mechanics of flight, but also meteorology, navigation by landmarks, and emergency procedures. The first generation of flight instructors were themselves veteran pilots, often bearing scars from early experimental flights. The very air, once just an empty space, became a resource, a medium for movement, and a strategic asset. Number 6. War became a whole new nightmare. Leonardo's mind, though often turned to art and the gentle mechanics of nature, also delved into the brutal realities of conflict. His designs for war machines, once theoretical marvels, found fertile ground among the constantly warring Italian states and ambitious European monarchs. The mass production of these engines of destruction reshaped battlefields with terrifying speed. The carro armato, or armored car, was perhaps the most visually shocking. Imagine a low, tortoise-like wooden wagon heavily reinforced with metal plates and bristling with cannons or breech-loading arquebuses pointing in multiple directions. Propelled from within by a team of men turning cranks and gears, these mobile fortresses first saw action under the Sforza banner in Milan around 1510. Their initial impact was psychological. Horses reared and threw their riders in terror, and infantry lines broke before the inexorable smoke-belching advance of these terrestrial monsters. Early models were slow, cumbersome, and vulnerable to bogging down in mud or being overwhelmed if isolated. But workshops in Milan and later in Brescia, a city renowned for its armorers and metalworkers, refined the designs. Lighter, stronger metal alloys were developed. Gearing systems were improved for slightly better speed and maneuverability. Ventilation, a critical issue for the crew inside who choked on gunpowder smoke and their own exertions, was addressed with baffled vents and even rudimentary bellows systems. By the 1520s, these armored wagons were a standard component of any well-equipped Italian army. They acted as mobile bastions, used to break enemy formations, protect advancing infantry, or provide covering fire during retreats. Their presence necessitated new tactics. Infantry learned to target the vision slits or wheels, and artillerymen developed specialized shot to crack their armored shells. Alongside the armored car came improved artillery. Leonardo's designs for multi-barreled cannons, often called organ guns due to their resemblance to a rank of organ pipes, allowed for a rapid volley of fire that could decimate packed ranks of soldiers. These were not simply single cannons grouped together, but integrated firing systems with shared loading mechanisms or faster reloading sequences. Foundries that once cast church bells now turned their skills to these fearsome weapons. The ability to lay down a concentrated field of fire changed the nature of infantry assaults. Massed charges against positions, defended by organ guns, became suicidal. This, in turn, spurred the development of more sophisticated field fortifications and siege techniques. Leonardo also conceptualized giant crossbows and catapults of immense power. While gunpowder artillery was becoming dominant, these mechanical artillery pieces still found a niche. They could hurl massive projectiles or incendiary devices with considerable accuracy and without the vast plume of smoke that betrayed the position of gunpowder cannons. Workshops specializing in these siege engines produced them for armies laying siege to fortified cities. The psychological effect of a flaming projectile the size of a small barrel arcing through the sky was considerable. Even naval warfare felt the impact. Leonardo's ideas for ships with rams, protected ore banks, and even rudimentary double hulls were explored by Venetian and Genoese shipwrights. His sketches for devices to attack ships from below, like drills or explosive charges delivered by divers, a topic for another revolution, hinted at a three-dimensional naval battle space. The scimitar chariot, a war wagon with rotating blades, proved less practical on the uneven battlefields of the time, but its underlying principle of mechanized area denial influenced the design of other defensive obstacles. The production of these war machines created a new class of military engineer and technician. Armies now required skilled mechanics to maintain and repair the complex machinery in the field. The demand for raw materials, iron, bronze, quality timber, gunpowder surged, affecting economies and trade routes. Espionage became critical, not just for troop movements, but for stealing the latest designs in military hardware. The battlefields of the Renaissance, already bloody, became louder, smokier, and more terrifyingly efficient in their destructive capacity. Traditional chivalric notions of warfare eroded further as impersonal machines came to dominate engagements. Fortifications changed too. Castle walls grew thicker and were angled to deflect cannonballs, a direct response to the improved siege weaponry emanating from Da Vinci-inspired armories. The age of the knight in shining armor charging with a lance was rapidly drawing to a close, replaced by the grim reality of mechanized death. Number 5. Cities start working like clockwork. Leonardo's genius extended far beyond the dramatic arts of flight and warfare. He was also a visionary urban planner and civil engineer. His concepts for multi-level cities, efficient water management, and improved sanitation when put into practice through coordinated civic projects began to transform the very fabric of Renaissance urban life. While no city was entirely rebuilt from scratch, according to his grandest visions of segregated traffic and elevated walkways, key elements were adopted and adapted, particularly in cities like Florence and Milan that prided themselves on innovation and civic pride. Water, the lifeblood of any city, was a primary focus. Leonardo's studies of hydraulics led to the design of more efficient canal locks, water wheels, and pumping systems. In Milan, under Ludovico Sforza, existing canals were deepened and extended using Leonardo-designed dredging equipment, some of which incorporated early versions of Archimedes' screws for lifting spoil. This improved navigation for trade barges and also enhanced the city's defenses by creating wider moats. More importantly, these canals managed by new water boards provided a more reliable supply of water for mills, tanneries, and other industries, as well as for public fountains, and in wealthier districts, even rudimentary piped water to private homes. His designs for water-powered machinery were implemented in civic waterworks, lifting water to higher elevations than previously possible with simpler systems. Sanitation, a perennial problem in crowded Renaissance cities, saw gradual but significant improvements. Leonardo had sketched ideas for interconnected sewer systems. While a complete overhaul was too ambitious for most cities, newly constructed districts or redeveloped areas began to incorporate covered drains and more organized waste disposal, moving away from the simple dumping of refuse into streets or rivers. Public latrines, Designed with better ventilation and flushing mechanisms, using diverted canal water became more common. These changes, though incremental, began to reduce the prevalence of waterborne diseases in areas where they were implemented. Connection between clean water, waste disposal, and public health, which Leonardo intuitively grasped, started to become a matter of civic policy. His ideas for prefabricated housing components and standardized building elements also found purchase. While not full-scale prefabrication as we know it, workshops began to produce uniform window frames, door sets, and even sections of timber framing. This sped up construction and repair, particularly after fires or during periods of rapid urban expansion. It also led to a greater regularity in streetscapes, though individual ornamentation still flourished. Architects and builders, working from pattern books influenced by Leonardo's principles of proportion and efficiency, created more harmonious and functional urban spaces. Leonardo also envisioned systems for managing traffic flow with separate levels for pedestrians and wheeled vehicles. This was largely too radical for existing city structures, but some wider thoroughfares were designated for heavy carts, while narrower alleys were reserved for foot traffic, a simple form of traffic management. His designs for bridges, particularly those using truss structures for greater strength and span, were adopted for crossing rivers and canals, replacing older, more precarious wooden bridges. These new bridges could support heavier loads, further aiding commerce. Organization of public spaces also benefited. Leonardo sketched layouts for marketplaces that were more orderly, with designated areas for different types of goods, better drainage, and shelter from the elements. Some cities began to implement these rationalized market designs, making commerce more efficient and the spaces themselves more pleasant. His understanding of mechanics also led to improved civic machinery, more powerful cranes for construction, better public clocks keeping more accurate time, and even systems for theatrical productions in public squares, using his insights into stage machinery. The cities of the mid-16th century, particularly in northern Italy, were cleaner, more orderly, and more functional as a direct result of applying Leonardo's engineering principles on a wider scale. They were not utopian, but they were measurably healthier and more efficient places to live and work, with public works departments taking on new responsibilities for infrastructure previously unimagined. Number 4. The deep, dark sea gave up its secrets. Leonardo's inquisitiveness did not stop at the water's edge. It plunged right beneath the waves. His designs for diving suits, underwater breathing apparatus, and even submersible vessels, initially conceived perhaps for naval defense or attacking enemy ships, opened up entirely new possibilities for underwater exploration. The Venetian Republic, with its intimate relationship with the sea, was a natural crucible for these inventions. By around 1510, specialized workshops, under the secretive oversight of the Venetian arsenal, began to construct and test Leonardo's aquatic devices. The first practical diving suit was a leather affair, made as waterproof as possible with greases and oils, featuring a helmet with glass viewports and air supplied from the surface through reinforced tubes. These tubes, often made of leather and wire, were connected to bellows on a support barge, diligently pumped by a surface crew. Early dives were shallow and fraught with peril. The dangers of pressure, the bends, though not understood as such, and equipment failure were ever present. Yet the ability for a human to remain underwater for extended periods, even just 10 or 15 minutes at a time, was revolutionary. One of the first applications was in harbor maintenance and construction. Divers could inspect ship hulls for damage without needing to careen the entire vessel. They could clear debris from harbor bottoms, lay foundations for new quays and seawalls with greater precision, and even attempt to salvage valuable cargo from shallow wrecks. In Venice, divers were employed to inspect and repair the submerged wooden pilings upon which much of the city was built, extending the life of critical infrastructure. The city's famous canals were dredged more effectively, using teams of divers to guide dredging equipment and dislodge stubborn obstacles. Leonardo had also sketched ideas for a submersible craft. While a fully autonomous submarine was beyond Renaissance technology, manned, tethered diving bells became a reality. These were large, heavy containers, open at the bottom, which trapped a pocket of air when lowered into the water. Men could sit inside these bells, breathing the trapped air for a surprisingly long time, and work on the seabed or inspect underwater structures. These bells were used for more ambitious salvage operations, allowing workers to attach lifting cables to sunken cannons or anchors. Naval warfare applications were, of course, a primary driver. Divers could attempt to sabotage enemy ships at anchor by drilling holes in their hulls or fouling their rudders. The Venetian arsenal experimented with mine layers, divers who would attempt to attach explosive charges, rudimentary gunpowder devices in waterproof casings, to the hulls of enemy vessels. While risky and often suicidal, the threat itself was a new dimension in naval defense and attack. Coastal fortifications began to incorporate underwater obstacles designed to be emplaced and maintained by these new underwater engineers. The exploration of the marine environment itself was an unexpected byproduct. Though not systematic scientific expeditions, divers brought back reports of strange sea creatures, underwater plants, and the topography of the seabed in coastal areas. Naturalists and scholars previously limited to what washed ashore or was caught in nets gained access to first-hand accounts and even preserved specimens from the shallows. This sparked new interest in marine biology, and artists began to depict underwater scenes with greater, if still somewhat fantastical, accuracy. The production of diving equipment created new industries. Specialized leatherworkers, glassmakers for strong viewports, and metalworkers for helmets and weights were required. Manuals were written and jealously guarded on diving techniques, safety signals, and the maintenance of the apparatus. The physiological effects of diving also became a subject of study, albeit rudimentary. Physicians noted the ailments that afflicted divers, attempting to find remedies, slowly building a body of knowledge about humans operating under pressure. By 1540, the coastal waters of the Mediterranean were no longer an opaque barrier. They were a realm that could be entered, worked in, and explored. Thanks to the practical application of Leonardo's underwater visions, this ability to operate beneath the waves gave states like Venice a significant, if often unseen, advantage in trade, defense, and engineering. Number 3. Machines did the work, and people watched. Leonardo da Vinci's notebooks are filled with designs for automated machines and devices that could perform repetitive tasks, a testament to his understanding of mechanics and his vision for labor-saving inventions. While the full realization of a robotic workforce was centuries away, the mass production of some of his more practical automated systems, particularly in textile manufacturing and milling, began to reshape labor and industry in the early 16th century. Guilds, initially resistant to changes that might threaten traditional crafts, were eventually won over by the sheer increase in productivity and profit, or were outcompeted by those who adopted the new methods. The automated loom was one of the most apale bio. Leonardo had sketched complex looms that could weave intricate patterns with minimal human intervention. Beyond setting them up and supplying thread, workshops in Florence and Lucca, cities famed for their silk production, invested heavily in developing and producing these machines. By 1525, large halls filled with rows of these improved looms clattering away, powered by water wheels or, in some cases, by teams of strong laborers working in shifts on large capstans. A single skilled weaver, instead of operating one loom, could now oversee several automated looms, primarily watching for thread breaks or mechanical issues. The result was a dramatic increase in the output of textiles, particularly complex brocades and velvets that were previously incredibly time-consuming and expensive to produce. Price of these luxury fabrics fell, making them accessible to a wider segment of society beyond the wealthiest nobles and clergy. This, in turn, fueled demand, creating a larger market. While some traditional hand weavers found their skills devalued or their employment precarious, new jobs emerged. Mechanics to build and maintain the complex looms, engineers to design improvements, and workers to prepare the vast quantities of yarn required. Textile industry, a cornerstone of many Italian economies, became more capitalized and factory-like in its organization. Similar automation was applied to other industries. Leonardo's improvements to milling technology, more efficient water wheels, better gearing systems for grinding grain or powering trip hammers, were widely adopted. This meant more flour could be milled with less human and animal power, contributing to more stable food supplies in urban centers. His designs for automated file-cutting machines, though complex, found use in metalworking shops, producing more consistent and cheaper files for artisans. He also conceptualized automated minting presses which, when implemented, allowed for faster and more uniform production of coinage, aiding commerce and state finances. Leonardo's famous robotic knight, designed to move its arms and head, while perhaps initially a novelty for courtly entertainment, spurred thinking about articulated mechanisms. While true androids were not a Renaissance reality, elements of its design, gears, levers, and pulley systems to create lifelike motion influenced the creation of sophisticated automata for clocks, public displays, and even theatrical special effects. These automata, while not productive in an industrial sense, coquette the potential of mechanical ingenuity and further normalize the idea of machines performing complex actions. The societal impact of this early automation was mixed. On one hand, it led to increased production, lower prices for some goods, and the creation of new skilled professions. On the other, it caused displacement for some traditional artisans and led to a concentration of production in larger, more capitalized workshops. The nature of work itself began to change, with some tasks becoming less about skilled manual labor and more about supervising and maintaining machinery. This shift was not always smooth and led to social tensions in some areas. However, the sheer economic advantages offered by increased efficiency meant that the adoption of these Da Vinci-inspired automated systems continued to spread. Cities that embraced these technologies often gained a competitive edge in trade. The whir and clatter of machines became an increasingly common sound in the industrial districts of Renaissance Italy, a precursor to the much larger industrial revolutions to come, all sparked by Leonardo's belief that machines could and should bear more of humanity's burdens. This also spurred a greater need for precise drawings and plans, leading to a new appreciation for technical illustration and engineering as distinct disciplines. Number 2. Your own body became less of a mystery. Leonardo da Vinci's anatomical studies were revolutionary in their detail and accuracy, far surpassing anything previously known. He didn't just observe surfaces. He dissected numerous human cadavers, meticulously drawing muscles, bones, organs, and vascular systems. In our alternate timeline, instead of these notebooks remaining largely private, his key findings and illustration methods were recognized for their immense value and, with the help of the burgeoning printing press, disseminated, albeit in controlled ways, initially to medical schools and physicians. This did not happen overnight, as societal and religious mores surrounding human dissection were strong, but the undeniable utility of his work gradually overcame resistance, especially when championed by enlightened patrons or forward-thinking medical faculties. The mass production here was not of a physical invention, but of knowledge. Around 1515, a consortium of physicians and scholars at the University of Padua, a leading center for medical study, gained access to, or perhaps reconstructed from early copies of, Leonardo's anatomical folios. Recognizing their duty potential, they began a project to create engraved plates based on his drawings. These plates, capable of producing hundreds of identical highly detailed anatomical charts, were a revelation. Previously, medical students relied on infrequent public dissections, often poorly executed, and on ancient texts like Galen, which contained significant errors. Now, they had access to clear, accurate, visual guides to the human body. The impact on medical education was immediate and profound. Students could study the structure of the human body in unprecedented detail before ever witnessing a dissection. Understanding of physiology, though still in its infancy, was significantly advanced because the actual map of the body was now far more accurate. Surgical procedures, while still dangerous in an age without antibiotics or effective anesthesia, became slightly less haphazard. Surgeons armed with better anatomical knowledge could operate with more confidence and precision, knowing where major blood vessels and nerves were located. For instance, amputations, a common procedure, could be performed with a greater understanding of muscle groups and vasculature, potentially leading to better outcomes and faster healing if infection could be avoided. Leonardo's emphasis on observing and drawing directly from dissections also fostered a new empirical approach within medicine. Students and physicians were encouraged to verify what they saw in the printed charts with their own observations, leading to a culture of critical inquiry. This gradually chipped away at the unquestioning reliance on ancient authorities. His illustrations of the heart and vascular system, though not fully grasping circulation as William Harvey later would, were so detailed that they spurred intense debate and further investigation into how blood moved through the body. Production of these anatomical atlases also spurred advancements in printing and engraving. Capturing the subtlety of Leonardo's sfumato and the precision of his lines required highly skilled engravers and printers. The demand for these accurate medical texts pushed the boundaries of print technology. Furthermore, Leonardo's method of depicting layered anatomy, showing structures from superficial to deep, became the standard for anatomical illustration. Beyond the universities, this knowledge, though slowly, began to filter out. Barber surgeons, midwives, and even artists gained a better understanding of the human form. Artists, in particular, could now depict the human body with even greater realism, not just its surface, but the underlying structures that gave it form and movement. This anatomical accuracy became a hallmark of late Renaissance art. Of course, this new knowledge did not solve all medical problems. Disease theory was still dominated by humorism, and treatments remained largely ineffective for many ailments. However, by providing a vastly improved understanding of the body's structure, the mass dissemination of Leonardo's anatomical work laid a crucial foundation for future medical breakthroughs. It represented a fundamental shift from theory-based anatomy to observation-based anatomy. The human body, for centuries a source of mystery and often fear, began to be understood as a complex, knowable system. This demystification, in itself, was a revolution, empowering medical practitioners and changing humanity's relationship with its own physical form. Access to accurate anatomical charts became a mark of a well-equipped physician or a reputable medical school. Number 1. They literally weighed the wind and measured the earth. Leonardo da Vinci was not only an artist and engineer, but also a keen scientific observer, devising instruments to measure various natural phenomena. The wider production and use of his designs for hygrometers, to measure humidity, anemometers, to measure wind speed, provided new tools for understanding and interacting with the physical world, revolutionizing meteorology, cartography, and travel. These instruments, once curiosities, became practical tools in the hands of scholars, merchants, military planners, and even farmers. Workshops, often associated with clockmakers or scientific instrument makers, began producing standardized versions of these devices from around 1500. Leonardo's hygrometer, which often used a ball of wool or other absorbent material whose weight changed with humidity, was refined to be more sensitive and durable. These instruments were installed in observatories, by agricultural estates, and even on some ships. For the first time, there was a way to quantify atmospheric moisture. This data, collected over time, began to reveal patterns. Farmers could make more informed decisions about planting and harvesting, and physicians started to correlate humidity levels with certain ailments, leading to early, though often simplistic, environmental medicine. The anemometer, typically designed by Leonardo with rotating vanes, allowed for the measurement of wind speed and, with a wind vane, direction. These became invaluable for mariners, providing more precise information than simply observing the state of the sea or the fluttering of a flag. On land, architects and engineers used them to assess wind loads on buildings and structures, particularly important for the increasingly ambitious domes and towers of the era. Windmills, already a vital power source, could be designed and sited more efficiently using data from anemometers. Military commanders used wind data to plan the use of incendiary projectiles or to predict the drift of smoke on the battlefield. Leonardo's odometer, a device that clicked over to record distance as a wheeled carriage moved, was a boon for cartography and travel. Attached to survey carts, these instruments allowed for much more accurate measurement of roads and distances between locations. This data fed into the creation of new, more precise maps. Merchants could better plan trade routes and estimate travel times and costs. Military logisticians could more accurately calculate march times and supply needs. The production of these odometers, requiring careful gear cutting and assembly, further spurred the craft of precision mechanics. Beyond these specific instruments, Leonardo's general approach to systematic observation and measurement was influential. His designs for various lenses and optical devices, while not fully realized into telescopes or microscopes in this accelerated timeline, improved existing optical aids like spectacles and magnifiers. Surveyors used improved sighting devices based on his principles, leading to more accurate land measurement and boundary demarcation. His understanding of hydraulics also led to better instruments for measuring water flow in rivers and canals, crucial for irrigation and water management projects. The cumulative effect of these instruments was a world that was becoming increasingly quantified. What were once subjective observations, it feels humid today. The wind is strong, it's a long way to Rome, could now be expressed with numbers. This fostered a more empirical mindset, not just in scientific circles, but in commerce, agriculture, and governance. Data collection, however rudimentary, by modern standards, began. City-states started to keep records of weather patterns, hoping to understand their impact on harvests and health. Road atlases, with distances verified by odometers, became more reliable. This ability to measure the environment fostered a sense of mastery and understanding. It also highlighted variability and change, leading to new questions. Why did humidity vary so much? How did wind patterns shift with the seasons? The tools Leonardo provided, once widely available, did not just provide answers, they provoked deeper inquiry. The Renaissance, already a period of immense intellectual ferment, gained a new set of instruments to probe the workings of the physical world, leading to a more detailed and nuanced picture of the Earth and its atmosphere. This was a quiet revolution measured in degrees, paces, and rotations, but its impact on how people understood and interacted with their world was profound. The world became a more knowable, more navigable, and more predictable place, one measurement at a time.